Oh, hello, good evening. You should be able to hear me clearly now. Let me know if you can hear me loud and clear. How about now? Can you hear me loud and clear now? Good evening. Can you hear me loud and clear now? Use the chat box and let's know if you can hear loud and clear. Okay. So, in our chemistry lesson, we were explaining the conceptual theories of acid and base. So we look at the contributions of different scientists to the concept of acid and base when we started the topic sometimes last week. So among the scientists is the scientist who is referred to as Arrhenius. Okay, he defined an acid as a substance that will produce hydrogen ion in aqueous solution. He said an acid will produce hydrogen ion in aqueous solution and a base as a substance that will produce hydroxide ion in aqueous solution. So this was the contribution of Arrhenius in his concept of acid and base. Then we proceeded to explain the contribution of Bronsted and Lowry, another theory of acid and base. They have Bronsted, Lowry, different scientists. They also gave us their own contributions of acid and base. So they define acid, in terms of proton. And they define an acid as a proton donor. They said an acid is a proton donor, okay? And a base is a proton, acceptor. They define a base as a proton, acceptor. So they gave us the definition of acid and base with respect to proton. Those are the contributions of these scientists. So we look at, examples, various examples and illustrations of these two. And we said that this the products of Bronsted, Lowry, and acid are known as the conjugate substances. Okay, the product of conjugate acid and bases. So they are known as the conjugate substances. For instance, we have ammonia reacting with water. Okay, so in the forward reaction, we got ammonium ion plus OH minus. So you can be asked that which of these species, this, or this is an acid, which one of them is a base, which one of them is a conjugate acid, which one of them is a conjugate base. So we always get the conjugate substances at the product side. Okay, the conjugate substances will always be at the product side, while the acid and the base would be at the reactant side. So now one of these two is an acid, one of them is a base. And we said an acid is a proton donor. So which of these two is donating proton? Is it ammonia? Is it water? Initially, water has two hydrogen. By proton, we mean hydrogen. So water has two hydrogen and is able to donate one of its hydrogen to ammonia, and ammonia has become NH4. So the proton donor here is water, which means is the acid, while ammonia is the proton acceptor, which means ammonia is the base. Okay? So now, an acid will always give us the conjugate base. So which means that the OH minus here is the conjugate base, okay, formed from an acid. And this NH4 minus is the conjugate acid, okay? This one is the conjugate base, while this is the conjugate acid. NH4 positive is the conjugate, acid formed from the base. And conjugate acid is a substance that is capable of donating proton. Conjugate base is capable of accepting proton. Are we together? Can you hear me loud and clear? All right. So now, we proceed. So there are limitations to Bronsted-Lowry acid and base. Now, what are its limitations? What are the limitations to Bronsted-Lowry acid and base? Now, first, the Bronsted-Lowry acid and base fails to explain the reaction between basic oxide and acidic oxide. So basic oxide, they are oxide of metals. Okay, oxide of metal, we refer them to as basic oxide. Example, sodium oxide is a basic oxide, okay, which is a base. Another basic oxide is your potassium oxide, okay, oxide of metal. We call them basic oxide. Then the acidic oxide, which are also known as the acid anhydride, they are the oxide of non-metals, okay? So for instance, carbon is a non-metal, then the oxide, carbon 4 oxide, carbon dioxide, is an acid anhydride, is an acidic oxide, okay? So Bronsted and Lowry failed to explain to us the reaction between basic acid and acidic oxide, basic oxide and acidic oxide. Then quickly, it also failed to explain the acidic character of aluminum chloride, boron, boron fluoride or thorium trifluoride, and iron 3 chloride. These are also acid. according to the net scientist, which is known as Lewin, okay, G.N. Lewin. So Brusted and Lowry failed to explain the acidic character of these three acids. So just make sure you know the limitations of these individuals. Now, the third theory that we would look at with respect to acid and base is the Lewis theory. So what is the contribution of, Gilbert Lewis? What is the contribution of this man to acid? So he gave us the definition of acid and base in terms of electron configuration. Okay, so you have to understand the concept of your electronic configuration. So you would be able to understand Lewis acid and base. So according to his theory, excuse me, an acid is a substance. He defined an acid as a substance that accepts lone pair of electron. Okay, that accepts electron lone pair. That is his definition of acid. So he gave us definition of acid and base in terms of, electron lone pair. Ionas gave us the definition of acid and base in terms of hydroxide ion and, hydrogen oxide. Then Lewis and Brusted give us the definition of acid and base in terms of proton. Why Lewis explain acid and base in terms of electron lone pair? Okay, so what did he say? He said an acid is a substance that accepts an electron lone pair. An acid accepts electron lone pair. And a base, okay, and a base as a substance that donates electron lone pair. Okay, he said a base is a substance that is capable of donating electron. All right. So for a substance to behave as a Lewis acid, it must be deficient, okay, in electron, and they are known as electrophile. Now, when we say electrophile are substances that are deficient in electron. Now, phile, when you hear the word phile, it means affinity, it means love. So when we now say electrophile, okay, meaning those substances that love electron, those substances that love electron, we call them electrophile. Because they don't have electrons, so that is why they love electrons, so they are called electrophile, because they don't have electron. It is what you don't have that you love, so that you can have it. So Lewis acid are electrophile. Lewis acid, they are electrophile because they are lone pair of electron acceptor. They accept lone pair of electron. Is this clear? Are you following? Do you have any question? If you have any question, you can use the chat box. Let me check the chat box if we have anyone asking question. Any question? Okay, somebody dropped a question. Say, okay, sir, a question, sir. Person say, is there any theory that supports H2O as an acid? Yes. Okay. A theory that supports water as an acid is this Bronsted-Lowry acid. In fact, water is an amphiprotic substance. Water is an amphiprotic, okay, substance. Water is an example of amphiprotic. When we say amphi means dual, okay? Protic, that is proton. So water can act both as an acid and as a base. Any substance that can act both as an acid and as a base, we call them amphiprotic substance. So look at this reaction between water and water. When water reacts with water, okay, one of the water will donate proton to this, and it's going to become, H3O positive. Now, then this one will now remain OH plus OH minus. Now, one of the water here it's acting as an acid, and one of the water here is acting as a base. So we have this as a conjugate acid because it has enough proton, and this is a conjugate base. So now water is an acid, okay? Water is acting as an acid, and at the same time it can act as a base. So water is an acid, water can also be base. So which is why we said it is an amphiprotic. Water is an example of amphiprotic substance, okay? I think ammonia is also another example of amphiprotic substance. Did I answer your question, Jerry? Now, let's quickly proceed with this. Now, these are examples of Lewis acid. Aluminum chloride. I will show you why they are Lewis acid. Barium trifluoride and beryllium chloride. Okay, they are examples of Lewis acid. Now, let's take one of them, aluminum chloride. How is aluminum chloride an example? Why is it a Lewis acid? Now, it defines, an acid as a substance that is capable of that is capable of accepting lone pair of electron, okay? So which means for a substance to act as a Lewis acid, it must be deficit of lone pair of electron. Now, aluminum has electron configuration 283. So in the outer shell of aluminum, it has 3 electrons. 1, 2, 3. And 3 chlorine, okay, in its compound. Chlorine needs 1 electron, okay, to form bonds. So we have Cl, okay, forming a covalent bond with the aluminum and that. Now, when you look at the molecule or the atom of aluminum, there is no any free electron at all around it. So as a result of that, which is the central atom there, aluminum is the central atom. So it is deficit. It needs a lone pair of electron. Aluminum needs a lone pair of electron. Okay, so that is why it's a Lewis acid. So it defines an acid as a substance that accepts electron lone pair. Okay, why a base is a substance that donates electron lone pair. So now I said Lewis acid are electrophiles, meaning they are electron lovers. That's why they, accept. Now, Lewis base, for a substance to behave as a Lewis base, it must possess at least a lone pair of electron. For a substance to behave as a Lewis base, it must have at least a lone pair of electron. Okay, so meaning that Lewis base, they have enough electron, they have lone pair of electron. So they are also known as nucleophile. Nucleophile are just like opposites of electrophile. Electrophiles, they are deficit of electron, they don't have electrons, so they need electron. Nucleophile, they have enough electron, they are rich with respect to electron. So meaning that Lewis bases are nucleophile. Okay, Lewis bases are nucleophile. An example of Lewis bases is your water. Water is acting as a base in terms of Lewis theory. And then ammonia is also a Lewis base. Now let's look at how one of them is a base. Now let's show how water is a base. Now this is water, H2O. We have hydrogen, okay, forming a covalent bond with oxygen. Okay, let me write this here. We have two hydrogen atoms forming a covalent bond with oxygen. Electron configuration for oxygen is 2,6, which means it has 6 in its outer shell. And using the orbital configuration, we have 1s2, 2s2, and 2p4. Okay, so now when we distribute the shells, this is oxygen, you have 2p4. These two electrons will be together in oxygen. Okay, then this 4, p has 3 degenerate orbitals. So you can write the p orbital here this way. 1, 2, 3. Then you fill the orbitals. You single fill before you double fill. So these two electrons are also together. You fill them this way. Then this this electron is standing alone. You put it here. And then this electron alone, you put it here. Then you bring down the two hydrogen. This is oxygen. Don't forget. Then you bring this hydrogen with your single electron and the second hydrogen. So they form bond, and these also form bonds. Now, this is the lone pair of electron. In water, rather, this is a lone pair of electron, meaning water has two lone pair of electron, so it can donate. So Lewis define a base as a substance that is capable of donating lone pair of electron or electron lone pair. So it has two lone pairs of electron. Look at one and look at the second one. So it's a proton donor. So water is a base with respect to Lewis. Are we together? Is this clear? If there is any other question, you can bring it forth. Question, let me check the chat box. Question, sir. I can say, is there any theory that supports against other four points? Now, this is yes, Jerry, water is an acid. Water can also act as a base. Okay, water can also act as a base. Is an example of amphiprotic. substance. All right, let's quickly proceed. So it also has limitation. What are the limitations to Lewis theory? One, it does not explain, okay, it does not explain the strength of an acid because it does not consider ionization. Okay, it actually does not consider ionization, that acid can ionize, base can also ionize. So it does not explain to us this concept of ionization. Okay, then also, according to him, according to the theory, neutralization of acid and base give rise to coordinate covalent bond. But neutralization of acid, that is hydrochloric acid and sodium hydroxide, does not contain any covalent bond. This will give us, you know, what we refer to as salt and water. But the neutralization in Lewis acid will give us a covalent bond, whereby this base, water, will donate its lone pair of electron to the acceptor, okay? Meaning the Lewis acid and base, when they react together, they will give you a product which will be a covalent bond instead of the traditional neutralization reaction. Lewis acids and base, we know that neutralization reaction is a type of reaction whereby an acid reacts with a base to form salt and water only. But meanwhile, Lewis acid and base, when they react, they give you coordinate covalent compound, a coordinate covalent bond instead of the traditional acid and base. So neutralization is a fast reaction and, instantaneous process, okay? But the coordinate covalent bond is very slow. So that is that. So those are all the definitions of acid and base. Sorry, let me move a bit faster. Now, we proceed to basicity. Basicity of an acid, okay? All acid produce hydrogen ion in aqueous solution, okay? All acid will produce hydrogen ion in aqueous solution. So the number of replaceable hydrogen ion, okay, the number of replaceable hydrogen ion in one molecule of an acid, the number of replaceable hydrogen ion in one molecule of an acid is known as basicity of an acid, okay? If we have, for instance, hydrogen fluoride, okay, and when it ionizes, it gives us hydrogen ion plus fluoride ion, okay? Now, when they ask you, what is the basicity of this acid, of this hydrogen fluoride acid? So the basicity is 1 because it's it only ionizes to produce one hydrogen ion. So the number of replaceable hydrogen ion in one molecule of an acid is known as, basicity of the acid. Is the definition for basicity of an acid clear? Comment in the chat box. Okay. Now, let's look at some of these examples to buttress on basicity. I want to give you a chart. So we have acid. So we're going to show it ionization. Then also we look at the basicity. And then basicity description. Now, this is hydrochloric acid. So when it ionizes, sorry, let me adjust it. Sorry, please. Now, we write the ionization equation for HCl. It's going to ionize to give us H plus and Cl minus. So it is only one hydrogen that has been replaced there. So if they ask you what's the basicity of hydrochloric acid, you say 1. And by 1, how do you describe it? You say it is monobasic. Okay, you say hydrochloric acid is monobasic. That is an example. Okay. So another example is your nitric acid, triazonitrate 5 acid. So when it also ionizes, it's going to give what hydrogen ion plus NO3 minus. It also ionizes to produce, one hydrogen, irreplaceable. So the basicity is also 1. The description, you say it is also monobasic. Then another example is your tetraoxophosphate 5 acid. So this is H3PO4. It ionizes to give you 3H positive plus PO4, 3 minus. PO4 3 minus. So the number of replaceable hydrogen ion there is 3. So you say the basicity is 3 because it has 3 hydrogen, and the remark say it is tri-basic. Okay. So another example is your sulfuric acid, that is tetraoxosulfate acid, which is H2SO4. It also ionizes to give you 2H positive plus SO4 2 minus. So the number of replaceable hydrogen ion there is 2. So basicity, you say 2, and that is di-basic. So they can just ask you or give you an acid and ask you what is its basicity. Okay, what is its basicity? So you should be able to tell. If you have question on this table, kindly put it in the chat box. Let me check that again. If you have question on it, do I still have something to mention? All right, yeah. Okay. Now, they gave a condition. They asked us to note something here, that it is not all the replaceable hydrogen present in a molecule of acid can be replaced with a metal. It is not all the hydrogen that is present in a molecule can be replaced with metal. Okay, so an example is your ethanoic acid. Please, this is ethanoic acid. Ethanoic acid, for example. So another acid is this ethanoic acid. It has a formula CH3 COOH. CH3 COOH. Now, it has total of 4 hydrogens, but when it ionizes, it is only one that can be replaced. So it's going to give us CH3 plus COO minus. So the basicity of this acid, one present in it that can be ionized. So it is monobasic. Okay, despite the fact that it has, 4 hydrogen, but it is only one of its hydrogen that can be ionized. So this means that ethanoic acid is a weak monobasic acid. Ethanoic acid is a weak monobasic acid. So we move quickly to group of acid, another subheading here. So groups of acid. Acid can be divided into 2 major groups based on their sources. So we have the organic acid and the inorganic acid. We have the organic acid and the inorganic acid. So what are organic acids? Okay, and these are acids. These are the acids, okay, that occur in natural products in plants and animals. So they are the acids that occur in natural products in plants and also in animals. So as a student, you should be able to give us examples of organic acid. You should be able to tell us and give us examples of organic acid. So this chart below will give us some example of organic acid and their sources. So you need to know example of organic acid and also their sources. All right. So example of organic acid is your lactic acid. So lactic acid is an organic acid. One, lactic acid is an organic acid. So what's the source of lactic acid? So you need to know the sources of all these acids. So the source for lactic acid is milk. So you will get lactic acid in milk. Then another example, if you ask to mention examples of acid. So citric acid is also an organic. It's also an organic acid that occur naturally. Okay, citric acid. So the source for citric acid, you see it in lime, okay, and lemon. Those are the sources of, citric acid. Another example of, organic acid is your ethanoic acid. Ethanoic acid, okay, which is known as acetic acid. also known as acetic acid, which is the common name. So what is its own source? In Vanja, Vanija, that is where you get it. You have to know the source together with the examples of organic acid. Make sure you know their source. Okay. So for another example of organic acid is your amino acid. Okay. Amino acids. So amino acids, we have 20 amino acids. 10 you can synthesize naturally, in the body, and the remaining 10 you derive them from food supplements. You synthesize naturally the non-essential amino acids in the body, while the essential amino acid you get them from food. So the source of amino acid is your protein. Okay, is your protein. Another example of organic acid is the fatty acid. Fatty acid. Okay, so what is the source of fatty acid? That is fat and oil. Okay, we have 5 examples of organic acid there. Then we also have another one making the 6th one, which is the ascorbic. Ascorbic acid, popularly known as vitamin C. Okay, so what is the source for ascorbic acid? So you get that in oranges, that is orange, in oranges. And then 6 examples, the 7th example now, we have the tartaric acid. The source of tartaric acid is green pepper and grape. So you can get tartaric acid in grape, or green pepper. And the last example making it is the butanoic acid. We see that in rancid butter, that has got rancid. Okay, so those are, um, the types of organic acids that we have. Don't forget we said group of acid can be grouped into 2, organic acid and inorganic acid. So we dealt with organic acid, and you know the sources of each of those organic acids. Now, next quickly is the inorganic acid. So they are also known as mineral acid. Another name for inorganic acid is mineral acid. Okay, mineral acid are also known as inorganic acid. They are prepared from inorganic matter or you know, mineral elements. So you should be able to tell us, example and the sources of these 2 forms of acid. I mean, examples and sources of inorganic acid. So, inorganic acids. Common example is your hydrochloric acid, HCl. Another one is your sulfuric acid, the tetrasulfase acid, H2SO4. Another example is your triazonitrate 5 acid. Another example is your, triazosulfate acid. So the sources, what is the source of hydrochloric acid? So you can get that from the rock salt. So hydrochloric acid can be obtained from rock salt. Then sulfuric acid can be obtained from sulfur by contact process or diffusion cloud chamber. Then, nitric acid, that's triazonitrate 5 acid. You can get it from triazonitrate, potassium triazonitrate 5. popularly known as 9. That's its own source. Then the source of this added sulfates is charcoal. Okay, charcoal. That is its own source of acid. Are we together? Can you hear me loud and clear? Chat box. Seems Jerry dropped something. H2 H2 or SO4 will be 2 basicity of acid. Yes. Yes, H2SO4 will be 2 basicity of acid. Okay, already answered. Okay. Okay. All right. All right. So that is what's it called? Um Groups of acid. And next should be strength of acid. Okay, but it's already 10 o'clock. So I need to stop there so that we will continue by God's grace. Okay, from strength of acid. Okay, our time is fast spent. It is 10 o'clock already. So if you have any question, let me quickly entertain one or two questions. Let me quickly entertain one or two questions. If you have any question, you can drop your question in the chat box. Any question? Browsing through to see if there is any question. All right. There is no any other question there. So let's call it quits there for tonight. Till we meet again by God's grace tomorrow. You have a pleasant night rest. Bye.